Welcome guys to our senior design presentation. My name is Caden Stefan, and we are G Cubed. Today we will be presenting our lunar regolith mitigation device, which utilizes a multi-layer shock shield. Here's an overview of our slides today and everything we're going to cover. And here's our team.
So let's start with the introduction of the project, what we have been working this semester. So we have been working on the Human Lander Challenge, which is all. Okay. We have been working on the Human Lander Challenge, also known as the HULC this semester. It is a competition which is managed by the NIA, National Institute of Aerospace, on behalf of NASA. So the 2024 HULC competition tasked a group of students to and their faculty advisors to design innovative solutions to address the mitigation of lunar PSI, which is the plume surface interaction. And at the end, like, each team was encouraged to submit an initial proposal. On basis of that initial proposal, 12 teams will be selected for the HULC forum in Huntsville, Alabama. And the project has an implementation target of 3 to 5 years. So let's start with the basics. Let's start with lunar regolith. Lunar regolith is a complex abrasive material, and it covers the entirety of the lunar surface. It consists of small jagged particles, and it ranges in size anywhere from like fine dust to larger rocks, like small and large boulders of several meters. It is primarily silicate based. It consists of inorganic materials. And when we did a breakdown of regolith by element, we found that it is 43% oxygen, 23% silicon, and 13% iron. So like, why do we want to do this? So let's talk about some reasons for lunar PSI mitigation. So regolith was found to be extremely fine and sharp, and like regolith sticks electrostatically to surfaces, and it negatively affects equipment functioning. It is also a concern in safety aspects. Like regolith sticks to spacesuits, it sticks to exploration vehicles, and astronauts found in the previous missions that regolith posed a real challenge for them. And regolith also has several health risks. You can get lung damage and cell damage. Right. So like for the project, like we had some design considerations to consider. So like for the HULC design, like it had to have minimal barriers for NASA adoption. It should not possess any additional risk to crew, and it should be a non-toxic solution. It was also preferred that it had minimal landings required, and like we would not require a go-around or anything to implement the solution. And like we had to assume that there is no pre-existing infrastructure on Moon. And the final point was it had to have the ability to operate in harsh lunar environments, that is extreme temperatures, vacuum, etc.
Now, keeping in mind our design constraints, we decided to alternate with two other designs that were possible and could technically provide a solution on a theoretical basis. The first of which is a silica paving, which is stored near the engine compartment and would create and harden into a landing platform. Once our HLS reaches an altitude of 100 meters, it would then deploy the silica particles into the rocket plume and eject them towards the surface. The next would be a handheld electromagnetic tool, which is energy-based collection and storage for targeted regolith on any instrumentation that is already affected. This works by funneling and vacuuming the regolith into storage compartments. Now, for the silica paving, this is stored near the rocket engines, and it has a separate ejection system that would then be ejected into the rocket plume and shoot towards the surface. Now, this simultaneously is heated by the rocket plume to begin the chemical reaction for a platform, and then it is ejected towards the lunar surface. Now, while this does address the plume regolith interaction before it becomes a problem, it does not have the most practical application because it needs an extra storage compartment in the propulsion system, and it needs a separate ejection device. It has insulation concerns being so close to the rocket nozzles. Additionally, it has a risk of rocket silica interaction, which may introduce some blockage to the rocket nozzles. Next slide, please. As for the electromagnetic tool, it acts as a funnel for regolith already disrupting equipment. This, as said before, collects and stores the regolith into separate storage compartments on the HLS. Now, this does not have the greatest application because it has energy and storage requirements. It also does not address the root issue as it needs to be affecting equipment already before it can solve the issue and vacuum any regolith affecting the equipment. Please. As a result, we decided to implement a variation of the Whipple shield as a more feasible and practical application to our design.
So our chosen design utilizes a linear actuated shielding mechanism that mitigates the lunar regolith interaction with the HLS. The next few slides will discuss various shielding mechanisms that were considered and the chosen design. These various shields operate on the principle that the collision with debris or some sort of particle with the shield, and the debris basically breaks up into smaller particles such that it becomes harmless to the actual HLS. So the first slide here will discuss two historical shield designs, the Whipple shield and the stuffed Whipple shield. These were first initially used for orbiting spacecraft to mitigate damage from incoming projectiles. They're implemented using one to several layers of sacrificial metal, usually made out of aluminum, and they're sometimes stuffed with like fibrous materials like Kevlar or Nextel. While these designs are still somewhat seen in spacecraft today, they're slightly more heavy and not as robust as some other designs. So some other designs currently being researched are the honeycomb panel and the foam panel shield. So the honeycomb panel has been used in other spacecraft, but it's slightly more difficult to manufacture. The foam panel shield, a more recent concept, is still being tested for its current capabilities. While these designs are a little bit more unique, since there's not much experimental data and they are a little bit harder to manufacture, they were not chosen for our design. So the eventual shield design that we chose was the multi-layer shock shield. So the premise on which these work is that there's staggered layers of Nextel, supported by rear metal wall. And the fact that the main layers are Nextel, the multi-layer shocks are generally lighter than Whipple and stuffed Whipple counterparts, which make them lighter while still maintaining the same manufacturability and robustness. And the overall intent and goal of this is to basically change it so that instead of the typical use being during orbit, we're going to try to reshape it so it's able to use during landing on the moon. And our specific design incorporates 4 layers of 440 Nextel and 1 layer of 2024 aluminum. And the Nextel layers are 0.53 millimeters thick, and the aluminum layers are 0.79 millimeters thick. All the layers are separated by a standoff distance of approximately 2.5 centimeters.
To apply our solution, we first had to design which spacecraft would be optimal to apply the actual shield. So 2 lunar landers were chosen by NASA to take humans back to the moon in the next few years. And we completed a trade study to determine which solution would be most applicable for our design. For this trade study, 4 parameters were analyzed: accessibility, thrust-weight ratio, technological feasibility, and design adaptability. Accessibility relates to how our solution impacts the human factors for each spacecraft. Thrust-to-weight ratio, as well as the mass of the spacecraft. With a greater thrust-to-weight ratio and greater mass, you have a greater margin in terms of how much mass can be added to the spacecraft without significantly impacting performance. Technological feasibility relates to the timeline of each spacecraft, and with a longer timeline and less mitigation being advantageous to apply our solution. And design adaptability relates to how well we can apply our design to the spacecraft, given the form factor, as well as the publicly available information. For our solution, we settled on the SpaceX HLS lander. This was due to 2 main reasons. One is that it has the greatest amount of publicly available information. With that, we can more easily design around the spacecraft without having to do too much guesswork or anything that would be unscientific. It also has a greater thrust-to-weight ratio and a much larger mass, and this allows for greater margin in terms of performance to add more mass to the craft for our solution. So
Moving towards our mechanical design overview, you may recognize this animation from our 90-second pitch video, which shows each mechanical subsystem of our design, which is the overlatch and raising mechanism, as well as the shields themselves and the actuation device that extends them to their upside down umbrella shape. So in the next few slides, we're going to break through a number of topics on how we came to some conclusions about our mechanical design. Firstly, we're going to talk about our ability to open and close repeatedly and have a reusable system. We're additionally going to talk about keeping the shields themselves flush to the body of the starship during when they should be stored. And we're also going to talk about protecting the shields from atmospheric conditions during Earth launch sequences. So as you can see, we used a linear actuator, and we chose this particular linear actuator through a series of trade studies. Fittingly, this is a system that has flight heritage and has been used in space historically, and has a stroke length of approximately 140 millimeters. We're using a linear actuator as opposed to any other like spring-based system because we want the system to be reusable, and we know linear actuators can open and close a set number of times in the hundreds of thousands. We're also housing it vertically along the side of HLS because, as you might notice, the linear actuator itself is pretty long in the actuation axis. So in order to maintain flushness, which we'll talk about in the next slide, we're storing it vertically in a custom fit strut. And with our geometry that's shown on the next slide, we have a actuation angle of 20.84 degree extension. So it's essentially the half angle of our upside down umbrella. So we're getting a 21-ish degree extension per each shield. Moving on, we have the hinging mechanism itself. As you can see on the left side of your screen, our hinging mechanism essentially has three collinear joints, which is not ideal for linear actuation, because if we had no other structures, our linear actuator, instead of pushing an extension and then pulling a de-extension, it would be stretching the Whipple shields. So instead of just using basic geometry, we're implementing a angled slotted hinge, which you can see on the top right, which allows for, at the beginning and end of actuation, the joint in the end of the linear actuator slides up and down the slot, angling the shield enough to where inertia and gravity for when we're on the moon and just inertia when we're traveling through space before landing will allow the shields to open and close fully without stretching or compressing the shields themselves.
The next part of our design is our latch raise mechanism. There are two main purposes for this mechanism. The first one is to protect the multi-layer shock shield from atmospheric effects during launch, and to raise and lower the overcover to allow the multi-layer shock shield to be extended and retracted for use in storage. There are 6 main components that create this latch mechanism. There's the platform nut, the lead screw, the end support, the moved BLDC motor, motor mount, and the overcover. Here we can see the orientation of each component of our latch mechanism. We decided in 2 lead screws to reduce equal distance from the center of the overcover to reduce the weight that a single lead screw sees to prevent shearing from the weight of the overlatch, and to prevent any rotation that would be seen from an imbalance of forces on the overlatch. And here we see our 2 orientations of our latch raise mechanism. Here on the left, we see it in the upper position, which would be used to allow the multi-layer shock shields to be extended for use. And here on the right, in the lower position for storage during transit.
So moving back to the whole mechanical structure as an entire system, here's our weight analysis, breaking down each subsection and then totaling it together. Of note, in these 3 main subsections as a whole, we don't use bolts or pins or fasteners because all of our main components are made out of a 4000 series steel, and the Starship HLS is also steel. So all the joints and such will be welded to the side of HLS We do use we do use fasteners for keeping the shields together within themselves, but that's not included here. Because these sections as a whole don't use fasteners to connect to HLS. So as you can see, the breakdown totals a weight of just under 11.6 metric tons, which is approximately 10% of the HLS's lifting capacity, which is well within the margins required for HLS's concept of operations, which is getting the payload to low Earth orbit, where HLS is then refueled before continuing on to the moon.
Okay, so when looking at the cost of our system, we had a little trouble getting the price of the Model S linear actuator and the BLDC motor, which is seen on the next slide, because it's not public information and I couldn't get in touch with the company. So we based the price of those off of similar items that are sold on resale websites online. A lot of our other components that are made out of like aluminum and steel, the price was based off of the raw material costs, and then everything else is accurate to how much it's sold online. We did opt out $800 for additional hardware, which would include nuts, screws, pins, all the little things, fasteners, etc. This gives us a total cost of $565,000 approximately, which is well within our budget.
For the structural analysis we performed on our system, we first consider what would be the most structurally intensive part of the mission, and that's going to be during takeoff. And the highest forces on the system are going to be on the latch because it's designed to take the aerodynamic loading, which is a longitudinal force. Additionally, the latch takes a G loading, which can be up to 6 times during takeoff, which is also longitudinal force. And then the Whipple shield itself will cause a lateral force as the G loading tries to bend the Whipple shield outward. And the latch mechanism has to support all of that, which totals a force of 40,500 newtons in the longitudinal direction and 17,800 in the lateral direction. This loading condition is then translated to the critical points we decided that were on the motor mounting bracket, which are the maximum shear and maximum bending locations. And that's because if the motor mounting bracket gives away, then the whole latch goes with it, and after that, the Whipple shield also. Using mechanics of materials fundamentals, we calculated the maximum bending stress will be 2.68 kilopascals, while the shear stress will be 14.6 megapascals. We put that into a stress matrix to calculate the principal stresses, which ended up being fairly close to that 14.6 megapascals because the bending moment is an order of magnitude less. To determine if our system can support those loads, we did a failure analysis. First, for the stress failure, we calculated the von Mises stress to be at 25.3 megapascals, while the maximum shear stress is at 14.6 megapascals. My bad. And both of those are less than the 4130 alloy steel yield stress of 460 megapascals. So we're not expecting any stress failure. And even accounting for that, welding can sometimes cut the strength of the material in half. It's still well within that margin. Additionally, that 25 megapascal stress is less than the 330 megapascal endurance limit for the steel. So we're also not expecting any fatigue failure.
Okay, so for our thermal analysis, we used a heat flux simulation in ANSYS Workbench to try to simulate the conditions that the Whipple shield, multi-layer shock shield will face during transit in space. We chose transit because it's going to experience both the extreme cold and then the extreme heat that may come from the radiation of the sun. We used a solar constant of 1361.1 watts per meter squared, and our model for the simulation mimicked the shape of the Whipple shield and had a weight average material property to make the analysis a little bit easier. So here you can see our thermal analysis. It kind of shows the temperature gradient, and could you run it through? Thank you.
Yeah.
Not a lot changes for this one, actually. it stays pretty consistent. Mine is at the bottom of the shield where the material is the thinnest, which is probably why it heats up the most. Yeah, if you double air them. Okay. And then this is our heat flux gradient. A lot more going on here, but again, it stays pretty consistent. This is when it hits the steady state. More heat flux towards the bottom of the shield because again, that's where the material is the thinnest. So for our results, we got that the temperature has a maximum of -224 degrees Celsius and a minimum of -270 degrees Celsius, which is still fairly cold. And the heat flux has a maximum of 1829.9 watts per meter squared and a minimum of -925.7 watts per meter squared. This is good because our melting temperature for the material inside of the multi-layer shock shield, the aluminum has a melting temperature of 506 degrees Celsius, and the Nextel has a melting temperature of 1800 degrees Celsius. So we don't expect any of the temperatures experienced during transit to change the performance of our shield during landing. One thing we did notice is that the temperatures in transit can vary from -270 to 77 degrees Celsius, but the operating range of the Moog Model S linear actuator is -50 to 80 degrees Celsius. So to try to keep it within operating range, we're going to use two methods of insulation, one of which is a multi-layer foam insulation blanket, which is a blanket that gets wrapped around the motor. And then the other one is a spray-on foam insulation, which will also go where the linear actuator is. The purpose of this is to try to keep the residual heat that comes from running a current through the linear actuator so that it stays within operating range.
So for our system's power requirements, the operating voltage and the max current draw for both the chosen linear actuator and the lead screw motor was found from the manufacturer's website. Multiplying those together outputs our peak power consumption. And then after finding our desired torque or motor RPM, you're able to calculate our duty ratio. For the linear actuator, we will be running it at the slowest speed to have the maximum amount of torque, which yields a duty ratio of 100%. And our lead screw motors will be operating at a duty ratio of 15%. Multiplying these together yields our average power consumption. And then multiplying those by a coefficient yields our anticipated heat dissipation power loss. Multiplying the linear actuator by 4 and the lead screw motor average power by 8, adding them together yields our operating power of 2.424 kilowatts. This is well below the estimated power supply of the HLS, which was found online to be estimated at about 175 kilowatts. And on the ISS itself, the International Space Station, it had a power supply of 76 kilowatts. So our operating power is well below our power supply. And then multiplying our operating power draw by our actuation time yields our energy consumption of 14.81 watt hours per cycle. So each time the shield opens and then closes. Next slide, please. Here is a simplified diagram of the electronics in our system with our linear actuator subsystem at the top and our lead screw subsystem at the bottom. Both the linear actuator and the BLDC motor will be controlled using a microcontroller unit as well as independent motor drivers. The BLDC motor itself utilizes 6 MOSFETs as well as 3 Hall sensors to ensure that it spins and operates correctly. And then the linear actuator and the BLDC motor will both be controllable from the cockpit so that the astronauts can manually deploy and close our system when desired.
To control all of our mechanical systems, we implement control theory. In our case, the applications of this would be to our latch mechanism and our linear actuator / extension mechanism. But we also have to consider why we include a controller in the first place. And the first reason for this is that we want smooth operation of both of our mechanisms. And secondly, we want to have precise actuation distance, be able to hit that actuation distance required without the use of limit switches. And the reason for this is to reduce the mechanical complexity of our system and have one less or increase the reliability by not relying on a mechanical component in favor of increasing the electrical complexity a little bit, since you already have microcontrollers, as we mentioned on the previous slide. So there are four controllers that we consider for our design. Number one being the bang control, two being the proportional control, proportional integral control, and then proportional integral derivative control. On the bottom right, we see our control law for the PID control, which we will discuss a little bit more in depth in the next slide. So as I mentioned, there are a couple criteria that we design for our controller selection. So of course, we want to design for smooth operation, and essentially what that means is that we want to minimize the amount of oscillation that we see. And with that, we eliminate the use of the bang control. Next, we want to minimize say error. And in that case, we would want to implement a integral control. Thirdly, we want a reasonable rise time, and in that case, we would want to implement a proportional control and an integral control. And with all those considerations, we choose a PID controller. So looking at our control law, we notice that we have to compute the derivative of the error function in addition to the integral. So with that, we use numerical methods in order to calculate that derivative for difference and trapezoidal rule. So of course, we also have to determine the actual gains, which are Kp, Kd, and Ki. And in that case, we need to use manual tuning. And a good starting point for that are the empirically derived values here, which were found in a paper which derived the transfer function of the system from the dynamics of a BLDC motor. Next slide, please. So as I mentioned, these are the transfer functions that were derived in that paper. And it's important to also consider what the inputs and outputs of the system are. So for the latch mechanism, the input is the applied voltage. For the output of the system, it would be the motor angular velocity. And for the linear actuator / extension mechanism, it's a little bit different, but pretty similar. So the input is still the applied voltage, while the output would be the linear actuator position. So with all that, thank you for attending our presentation, and we are now open for questions.
Great job.
I'll pull up the chat on Zoom so you can see
Yeah.
Tom's
It's pulled up.
is pulled up.
Yeah.
I'll put it on the screen.
Let me stop. Should I stop sharing?
Yeah, you're just gonna have to share the full screen.
Yeah.
Exit presentation.
Well,
Okay.
yeah, this way I can keep.
Okay, the first question.
Okay,
You can show
so
the question there, so everybody can see it. And also, before you answer any question, you read the question first, because when I put this video on YouTube, the chat message will not show.
okay, so the first question is, so what exactly are you trying to achieve with this design? Okay,
Okay, our main.
come up.
Mind,
You're in the shot, yeah.
Okay. Our main objective is to prevent our equipment from being contaminated with the regolith in the first place. Once the rocket plume interacts with the regolith, we are preventing it with the Whipple shield at an angle, defends the rest of the HLS from the vertical standpoint, from the bottom to the top, and it essentially deflects or breaks up the regolith on impact with the variation of the multi-shock Whipple shield. It's not really a Whipple shield, it's the multi-shock shield layers. The main purpose of it is to prevent the regolith from interacting with the HLS at all, which is why we have it oriented like an upside down umbrella, which is why we use Whipple shielding to maintain the regolith in one location instead of allowing it to spread to the rest of the ship.
So you need 0 regolith getting to the vehicle above your shield.
Zero regolith is a rather theoretical and ideal simulation. We don't know how feasible that is. In general, it's a very messy environment. But for the most part, yes, we are preventing any interaction with the rest of our HLS, with the rest of our vehicle. Thank you.
Can you show a Sure, yeah.
It might be best to play the
The
video
animation.
and then like pause it at the right time, because that'll be the most cut in shot.
All right, I'll play that. So you can see here, like when the latch raises, it's going to extend out with a linear actuator, and it's kind of making a approximately 21-degree angle with the body. Half angle.
So I can actually take this question with some amount of seriousness. So when we did computational fluid dynamics on as well as background research on what we're expecting, how we're expecting the plume to behave, we're expecting the plume to come directly from the bottom or directly from the outside of the crater we're creating, which itself I think was 1 or 2 diameters of just the diameters of the engines, which means we're essentially coming, the regolith is coming directly from below it. So hypothetically, for the areas not guarded by the landing legs themselves, on descent, the top of the rocket wouldn't get wet at all, wet in quotes. Where the bottom of the rocket that might get quote unquote wet is being built to withstand hot staging for HLS Starship. So the assumption that we made was if it can withstand hot staging, it can withstand getting sandblasted a little bit.
But you've got pretty big gaps.
Can you play the video a little more?
Yeah.
So additionally to our gaps, there's fine. We also are using the built-in structure of HLS to fill in those gaps. So any gaps in between the shields, once they spread out, a large majority of that is being defended by the struts and landing feet, as well as any direct from beneath. Regolith is being trapped by the underside of the overhang itself.
Can you show the shields all the way extended? That was a little further up in the video. Yeah. Because I'm just seeing big gaps. This is kind of showing the extension of the Whipple shield off the body, because it's
What is maximum angle?
20.84 degrees is the maximum half angle. So the angle between the HLS body and the shield at full extension is 20.84 degrees. And then we've got that on each side.
Yeah, that's that what it means. If it's only 20 degrees, there's a huge gap between.
Now, it's important to remember that this is still a design in progress.
I think
While it still has insane gaps, we have a much larger area protecting the HLS without the Whipple shield. You have about 80% of the surface area being protected with the Whipple shielding. That can obviously be improved upon in the future.
Especially once, if this design were to move forward, when we're made aware of what precise equipment is being protected and the location of that equipment on HLS, which is not currently publicly available, we can apply this concept to anywhere and everywhere on Starship once that information is made available to the public.
take the last. So you're saying if the retaining ring is sufficient to defend the gaps, why do you need the shields? So basically, like Ian mentioned earlier, when we were looking at the way the plume interacts with the regolith and how it impacts the vehicle that's landing, there isn't all just straight up. So we wanted to extend it out to make like an upside down umbrella, because there's still going to be some coming off the sides. It does spiral on the side of the body. So that will account for the spiraling. And then the ring that you're calling the overlatch, it can trap the I can trap the regolith that makes it behind the shield and keep that down as well. So it's doing both the vertical and keeping it within, so it doesn't travel further up on the body and damage important equipment.
I suppose the part about it that gets a little bit problematic, it's like when you have an impingement zone between the thrust, I guess the thrust wouldn't actually be there, right under the impingement zone, so. Never mind, I'm looking at from the perspective of Blue Origin Liner, I forgot you guys were using Starship.
Yeah, we're using Starship.
Answer the question first.
You guys want to take that, Hayden?
We entered the top.
Answered, yeah. I did answer that.
I'll re-answer to retaining.
Retaining question. Something much more full coverage.
Thank you for your suggestion.
I can take this one. Yeah, so essentially there's the HLS, it might be reusable. And so the key goal of this design is to see how we can increase the longevity of the spacecraft as much as possible. And so whenever you're coming down to land, there's a few instrumentation, there's star trackers, there's presumably some kind of LiDAR or radar system. Those all need to be protected, and essentially they're either looking up or they're looking down. And with the shield, we can guide the lunar dust into different locations on the spacecraft, or as well as just block them from specific locations. So protect the LiDAR, protect radar, protect star trackers. The things that are sensitive optical devices, those need to be protected, and that is the goal of the shield.
Yeah, I think I can take that one. So in terms of like getting the bases to touch and the tops to overlap when they're closed, so they become edge to edge in the open position. With the current location, low on the Starship body, that's not feasible due to the presence of the landing legs. So what we decided to do is kind of accept that gap, and understand and make the assumption that the foot pads and legs themselves are meant to be sandblasted and are expected to go through this regolith interaction. So any gaps that are created by the necessity of presence on the landing legs themselves are going to protect or be able to absorb that impact and that abrasion in any event.
The legs are not particularly wide relative to gaps.
The main problem we've had with that is that the main problem we had with that was that we don't entirely know the final iteration design of the SpaceX HLS. And there've been 3 so far iterations, one that is just a rumor as to what the legs might look like. And we just do not know what the final leg iteration of the Starship will look like. We put a relatively abstract version of the legs, but we aren't 100% certain what might be finalized on.
Okay, but you've made an assumption here and designed around it, and you still have really big gaps.
Yeah, I'm not sure.
So, I mean, I guess one thing I could say about that is if we're not making assumptions, we have very little information about the structure of Starship. So if we're going to sit around and wait for us to have access to all the designs of Starship, then we're not getting this done in a year or in a semester. So to the not making assumptions part, there in the umbrella analogy, if you have a radially expanding plume, which is coming from underneath the Starship, the feet themselves are much closer to the plume, so they're casting a larger shadow of protection along the sides of HLS, which means that even though these are 3 meters by 2 meters or whatever the final size might be, the protection shadow is much larger than just that 2 meter by 3 meters, in the same way that our shields themselves are protecting the entire top end of the Starship, even though they're only 5 meters tall.
What do you say?
It seems like you're assuming the particle paths are going to be basically two-dimensional.
I can maybe take that. The particle paths are going to be radial because the engines are radial, and so we expect like they're going to be just ascent. Like you can assume.
You said that.
Yeah.
Yeah.
Yeah. So like essentially we can just look at each plane. And because like I said, the engines are radial. This doesn't cover all the engines, but because essentially this doesn't cover all the engines, but there are engines that go the whole way around. If you could look at this slide actually.
Which one?
This one.
18. Okay.
So it's really hard to see them on because it's like low res, but essentially there's all the engines down here. There's 28 radially mounted engines up here. And so we assumed we assumed radial impingement.
Is that a reasonable assumption?
Yeah, that's
Turbulence, particle collision.
in zero, essentially whenever you don't have an atmosphere, we don't expect turbulence to occur. All the particle paths will be relatively linear after the impingement. There will be turbulence in the exhaust itself, but post impingement, there will be significantly less. And especially at a distance this far, the exhaust plume expands pretty significantly in vacuum.
Remind me how much mass this is. Okay. 20 something. Okay.
Yeah, I mean, in addition, I guess this is kind of everything you're asking for as far as I understand the question. It is a lot, but one of the reasons that we chose HLS Starship was because it has a super high, not super high, but it is a adequately high thrust to weight ratio. So adding 10% isn't expected to impact getting to low Earth orbit. Because the low Earth orbit lifting capacity is estimated to be between 100 and 150 metric tons. So this being about 10% of that, in addition to the Artemis equipment that is in the payload fairing and everywhere else on HLS, we're still able to get to low Earth orbit where Starship will then be refueled. So we understand that that's a lot, but in the grand scheme of things, it's still capable. So I see your point, and I raise you that there's a 50% margin in what we expect HLS Starship to be able to achieve anyway. Like all public estimates are between 100 and 150. So if they're shooting for 100, like that's on them, not us kind of thing. But if NASA's operating with the bare minimum of 100 tons to low Earth orbit, we can add this as long as Starship does their part.
Just real quick, when you say total Earth weight, but it's in metric tons, what do you mean by that? Is it kilograms? What are you?
A metric ton being 1,000 kilograms. But that would just be
weight. That's just mass.
Fair enough.
Just wanted to clarify because the units were, I don't know, it's confused me for a sec.
So I'm assuming a significant fracture of your mass is having this Whipple shield system fraction. Yeah.
The system, so I'm not understanding.
Zoom have the numbers in like the shield. I don't remember what slided onto the shield versus like the shroud.
6.8
Right
what?
there, incredible.
Yeah. Yeah, so the shock shield is the majority of the weight. So the purpose of having the multi-layer shock shield is so that it like contains all the regolith that impacts it. A normal shield would either fracture and cause a little more material to escape from it, or it'll just bounce off the regolith, but we want to try to contain that. Expected impact energy.
I'm not, I don't remember the exact energy, like the number. We expect up to 2 kilometers per second in small particles and up to 150 meters per second in larger particles, up to about a centimeter in size.
Yeah, and I'll kind of add, going off of that, I mean, all of the different shielding ideas that we researched had been tested in research papers with the impact energies for both lunar interaction and like particles in space. So our primary purpose for picking the multi-layer shock shield as opposed to like an actual thick shield is because it was, even though it is still heavy, it is like the lightest of the shield combinations that we found. Because a lot of the other ones are like stuffed with things which would just increase the mass more than we currently have.
What did he ask?
He said, I'm a little skeptical.
In terms of reusability, what can you expect from
In
something
the
like
final
this?
report, we can like do some reiteration, like how to minimize it.
Local shields are designed for micrometeorite impacts at huge velocities.
So. I guess I can take that one. In the same like the whole thing with micrometeorites at high velocities is we're gonna assume I don't have the numbers offhand. But the energy is, we'll say, approximately the same as a slower and heavier particle of regolith on Earth, on lunar landing. So with the same impact, or approximately the same impact energy, then Whipple shields would do the same thing in their current iterations as they would in our design.
Yeah, I guess adding to that, Whipple shields are also at least tested where the particles impact perpendicular, but ours acts as both a deflection thing because it is angled so high. So we anticipate a good amount of the regolith to deflect, and then we have it implemented as a Whipple so that if it is a high enough impact energy, it'll still act as one, but it won't take as much as of the brunt because it is not being impacted perpendicular.
I question whether the same physics are at play here. For example, the Apollo landers, they got sandblasted with basically no shielding, right? Yeah.
Yeah, but the Apollo lander, it was a one-time use scenario. They got sandblasted, but they got sandblasted. And so to protect optical equipment, we need to do that as much as we can.
He's asking how many holes got punched.
0. However, there was a survey or two mission which got significantly sandblasted with high impact velocities. And we used that research by Phil Metzger at University of Central Florida to gauge impact speeds and velocities as well as particle sizes, which is why we decided to go with the Bilpa shield over a smaller shield. And yeah.
What was your question, Garrison? Well,
Oh, it was the I was thinking about in terms of reusability, because we're gonna have to reuse the lander, so in terms of like, would there be maintenance required where you have to replace the shield every so often? Because if you're gonna have a ton of impact meteors, eventually you're going to have some sort of fatigue, cracking. I wouldn't know the overall understanding because I'm not a material science person, but it sounds like that would eventually lead to some problematic results after a while. Not to say that necessarily losing one is inherently bad, but after a certain amount of time, a certain amount of uses, eventually it could be problematic. So I just wanted to know your thoughts on like how long can these be sustained? Structurally, they'll be fine. I'm just curious as to like if we're gonna get a lot of impact, but
Yeah, so to Tom's point, in it, like to tack on to your question, if we're not expecting any holes to be punched, and we're just expecting it to be sandblasted, then we're kind of relying on only the first shield layer to protect everything. In which case, if that is the case, then we can always just, all right, the first one gets worn down, but now we have 4 more to go, which would allow multiple uses on one set. But based on the construction of our shield casing, just like the frame that holds the shields themselves are able to be replaced. So assuming that what you're saying and what Tom is saying is reflecting actuality, then we could just replace one or replace all of them every 5 moon missions, since that would be 10 cycles of getting sandblasted, 5 just being a number off the top of my head. And at that point we're past the life of Artemis.
Okay, he said, if I'm a program manager, I don't want multiple uses. I want to reduce those 11 tons.
this one. Because the redundancies are important, but like too many redundancies are, redundant. So.
Yeah, it needs to be more optimized. Because you mentioned that, I mean, what are the impact energy are you studying? And then you use that, you studied impact energy, then design like how thick or how strong it should be. It's not that the stronger the better, right?
I need glasses. What is he saying?
So people,
Format, but you could probably retire on this one.
okay, so why are we welding this onto the vehicle?
Are you asking why are we welding as opposed to using bolts and screws, or why are we attaching this to the HLS?
Yeah, bolts and screws.
I can go into that one. The Starship uses there's the skirt that goes on underneath, and then there's also the upper section where the latches happens to be located, or the beginning of the linear actuator happens to be located. That's located on the pressure vessel, on the actual tank pressure vessel wall. And so we didn't want to weaken that using fasteners or cause any leaks or anything negative like that.
That's not mean with cost leaks. I mean, the few sets that we use rivets, there's no leaks.
Fair.
Like, I mean, what is in the lower section of the HLS? Is there any like habitation, or is it all just like tanks and electronics?
It's just well, there's if you want to go like this, maybe that would work.
Mm.
Yeah, so like up here is the actual tank. Down here is a skirt. So the skirt goes around the engines. There's the thermal protection systems down there, and various structures. Up here is the actual tank. I don't remember if it's liquid oxygen or liquid methane, but the tank is located there.
But is the tank right up against the skin?
Yes, it's a single wall.
It's a single wall?
Yeah.
Okay.
Single wall pressure vessel.
It's like for building airplane wings. You don't put a tank in the wing for fuel. You make the fuel tank in the wing.
Yeah.
I don't like welding subsystems to the vehicle. Service and replacement can become difficult. Okay,
That's fine.
that's a fair point.
I guess in your guys' defense, I'm thinking about it in terms of like the replaceability, the only thing you're really looking to is replace the whipple. But then again, what you're actually gonna be welding to is the arms.
Yeah.
But I guess it's dependent on whether or not those arms can survive impacts after multiple uses, so.
Fair, but the arms are also directly behind the shield.
That doesn't mean you're not gonna be, experiencing extremely high turbulent environments. Might result in some sort of impact. There's always that possibility.
Can you flip to your budget slide? Yeah. So we have two budget slides. Do you want the one with the total cost or just more of a breakdown?
Let's go.
Hmm?
So you can see raw materials and components.
How is this getting put to, no, he's asking about how it gets put together.
She's asking about labor.
Yeah, labor. cost.
I mean, we can assume that the cost of labor for putting it together is gonna be the same cost that NASA spent on designing it, which was none, because we did it. So if this is truly a student project, why not go all the way? Also, we don't know the work price rates for NASA.
Also, our total cost is well below the given 1 million, so I think we won't go over budget if we choose to hire people as well.
Matter of fact, you guys are actually paying to do this work, so.
Yeah. But I don't think NASA's gonna let you guys out there with wrenches and hammers. They do.
SpaceX might.
never know.
Give us tip to use the one.
Slide 30.
Oh, it'd be fine.
Okay.
Thank you for numbering your slides, by the way.
Oh, that's temporary.
Loading condition on the latch.
There.
What's wrong with that? I'm not sure I understand your question. That's a lot of digits.
We just have really good precise measurement.
I can maybe go into that. It was an overshoot. Maybe we overestimated. However, this was
The signature is just too much.
Too many significant
Yeah,
digits.
yeah. So
Not that
There's no
accurate.
point to make it like.
He's saying like you could just write 18
Oh,
down.
okay. Okay. Cool.
Okay.
Gotcha.
You only get 6 figures.
Don't always punch it like that. Yeah.
Yeah, no.
Call it out.
Yeah, it would be 18,
Yeah.
31.
Maybe not even that.
What are we seeing a structural analysis of here?
So this would be the loading conditions at this point and this point. So we have the bending and shear stresses calculated for those 2 points of the motor mounting bracket.
Through the CAD model of that.
The motor mounting bracket.
Not in the PowerPoint at all.
24 should have it has a picture of it, but it's not.
Yeah, so the motor mount is number
It
5
would be
right here.
the top point and the side point. Yeah, so that big flat plate gets butted up to the HLS and welded onto it. Why is that the structure last we chose to show? We chose that because the lead screw mechanism is spec to support the entire weight of the mechanism. But we did not know if our attachment method was sufficient to support the loading. So we chose that point in order to determine if the latch would just break off entirely from the loading forces or not.
And also what you were saying earlier about how this motor mount comes off, then the latch comes off, then the shield come off, and that would be catastrophic.
Yeah. So most critical point.
Mhm.
Is that supposed to be a smiley face?
No.
No, that's a fair idea.
If you want it to be, yes.
It does actually.
And eyebrows?
Winky. It's the cyber motherboard from that PBS show.
Oh,
If you know your real one.
my,
Cyber Chase.
no, I don't.
Okay, I'd expect that the shield, the retaining ring, something in there would be critical.
So those are also important, but the shield itself doesn't experience much force during land off. It's just the individual particles. There's no like pressure there in terms of like atmospheric force. And then the retaining ring, that is something we considered, but because the force is distributed along the entire retaining ring, or I guess by retaining ring, you mean the overcover, I assume. The force there is distributed along that entire load and it gets concentrated to the mounting bracket.
Yeah, but it's also a long beam supported on the ends. It seems like bending would be a concern under the atmospheric loading at max Q.
I can talk about that as I did that.
Mhm.
So this overcover, it's also an aerodynamic shroud. The aerodynamic loading at max Q is on this shroud, and that was calculated beforehand, and ended up being significantly less than what would be experienced by that latch at that specific point. Yeah, the long beams for the ends. Yeah, I don't have the exact numbers, unfortunately. Maybe we should have included that,
How
but
is that thing attached to the vehicle? It's welded inside of the ring or, because if the bond current is different, the analogy is completely different.
Bring down to
Yeah.
25.
The lead screw itself is going through the cover.
So the screw is how you attach that one.
Yeah.
There's
Okay.
platform not attached to the.
Okay. You do have a problem. I cannot help. I thought it's welding. Then it's different.
Well,
No, it's not.
the connections are welded.
Which part is welded?
So the end support and the motor mount are welded to HLS.
Yeah.
And then the platform nut is welded, or not welded, it's bolted to the overcover.
So the overcover can slide up and down.
On the screw, on the lead screw.
Mhm. Okay, you've got a very low stress relative to both the static allowable and the fatigue threshold.
Yes, we do. The motor company said that they would work with whoever purchases the motor to design.
So,
Your structure is not optimized. That was too small.
Um.
Yeah.
Yeah, the weight really comes from just the fact that it's a very big Whipple shield. Like HLS is what, like 15 meters across or something, 9 meters, 9 meters across. So there's just a lot of material there. One of the things we would probably consider doing to try to cut weight is change materials. A lot of what we have is steel. So we can probably change that to something more lightweight, but still just as strong.
So another thing, the reason our thresholds are so high is because the parts being analyzed here are commercial off-the-shelf parts. And we're not gonna buy a motor mount and then cut it in half to reduce the area, to reduce the endurance limit. So if anything like that were to happen, we would be loading it higher in order to get closer to the limit. But we're not, we don't have the capability to alter commercial off-the-shelf parts.
I suppose if your shields are 10.9 tons, that's fair. Yeah,
I mean,
yeah.
I think throughout this process, we weren't aware that our weight would be, well, it was between 10-15% of our allowable weight for the HLS. We didn't really consider that in our material selection, based on the requirements we were trying to meet.
Do you have an analysis showing the probability of stopping debris going through? No.
so we kind of covered that in the 90-second pitch video, but we didn't put it on the slide. The projection of like debris going through a shield.
Yeah, but that wasn't.
Yeah, as far as the an analysis of stopping the debris, the only sort of analysis we have of that is just research papers which did impact testing on the different types of Whipple shields or shielding mechanisms that we researched.
I have to interject a little bit here. There's nothing wrong when you're giving a presentation like this of saying, I don't know, or we didn't consider that, just so you guys know. You don't have to have an answer for everything.
And just to clarify, we did consider weight. We just did not see our 10% weight of the total allowable weight to be as big of an issue as you have raised.
Yeah.
I think we can all in the room agree to see the point that we are overweight. But in the spirit of the challenge, which was to add something to it, this was the design we trade studied to figure out how we could best reduce damage due to regolith.
However, absolutely, you are correct. We definitely can work to reduce the weight, and we will definitely consider that moving forward for our final report.
We were simulating, the Whipple shield that's, not the Whipple shield, the multi-layer shock shield, which will be attached to the vehicle during transit. So kind of in between the Earth and the Moon. And the scenario we simulated was kind of like an extreme case where the entire front of the shield will be experiencing maximum solar, radiation. Yeah, we had this simulation run. We used the solar constant and a heat flux simulation. And when we ran that, no matter how long we ran it, it kind of stayed and kept the temperature at negative 224.12 degrees Celsius. It didn't heat up the material that much. Well, the ambient temperature in space is pretty low, so we were just accounting that that would keep the device pretty cold.
They're also, they're large panels that are very thin. So,
Yeah.
I mean, our calculations might be incorrect. But the way we kind of justified that being what we decided or what we came to as a conclusion, was there's heat flux in from the sun, sure. But there's also a very large surface area, which is, radiating heat back into the cold of space.
There's not a good mechanism to lose heat to that ambient environment other than radiation, and the sun is sending a lot more radiation to you than you're sending out to space.
Then I guess that much.
Yeah.
How do you get negative average heat flux? If your maximum much more positive.
Yeah. Okay, there's certainly gonna be spots that are much hotter than negative 224 degrees Celsius. Astronauts have cooling systems in their spacesuits for a reason. All right, yeah, I mean, we did our best on the thermal simulation. It's not something that we're very familiar with, but we'll work on that for the final report for sure. Okay. Our assumption was that it would get much warmer than our simulation showed, so we just wanted to make sure that there would be no affecting the material. From the research that we did, it kind of showed that like the lower end of the material, lower end of the temperature wouldn't affect material performance that much, so we wanted to focus on the high. It's more of like a warping concern. We don't want the shape of anything to get warped during transit, because that would make it harder to open up, and it wouldn't serve as great of a purpose if the shape is not no. Okay, I can see your point. It will likely happen due to plastic deformation, yeah. That is something, well, yeah, that's a good point. We'll take that into consideration for our final report.
Let's party down here. Sorry.
We'll take that.
Not going through the actuator. So you said you're going to use the power going through the actuator to keep it in its operating range, not during the entire transit. Just that when we want to use the linear actuator, we're gonna assume that it's frozen, and by running power through it and the actuator doesn't move, all of that power just goes into heat and it'll heat up the actuator. And then it'll get within operating range, and then it will begin to actuate. That is a good question.
There's not a lot of information about these actuators available online. We did try getting in contact with Moog to talk about their product a little bit more, but I never got a call or email back. Or maybe you need to do some active heating.
Yeah, we might need some active heating if the Moog people get back to us and say that the actuator will no longer function if it goes below -50 and then back up to -50.
that's not something we considered at this time.
It would also be dependent on what temperature we're expecting to hit, which you pointed out, any operational temperature that we think we might be getting, needs to be recalculated. So we couldn't cite any numbers on that.
Okay, thank you, Tom. Thank you so much.
Thanks, Tom.
Thank you, Tom.
So overall, great job. I think your structure analysis is wrong. Can you go back to the structure analysis, please?
Which part?
Next one? Yeah.
Okay.
I mean, what is the, why you have a tall X here?
That should be zero.
Right? Why you have a tall X here? And also, I mean, if it's the same force cost the sigma xs and tau xy, why your tau xy is so much higher than sigma xs? This does not make any sense. Why this one, the tau x, the shear stress so much higher than sigma xs? It doesn't, it really doesn't make any sense. I mean, when you calculate this result, you should specify that the calculation is wrong. Right.
Is this coming from the lateral and transverse forces breaking down that way?
And also, when you explain this one, I think back structure. You talk about like it's one shear stress is at 1 point. I think it's like shear stress 1 point, sigma is another point. Why you put stress component at different point in one matrix? That's absolutely wrong. When we have a static stress, the 3x3 matrix is a stress component at 1 point. You don't put like stress at different point in one matrix. I mean, what's the point to calculate in that way? Right? So the whole structure of this calculation wrong. And I'm still like confused about like your own shear stress. Yeah, take pictures at a different point. Yes, what I mean is that when you do the stress analysis, when you calculate like I think what you want to calculate is the principal stress, right? And then use the failure theory. But what you need to know is really find out the critical point and really like you can choose different point, but different points should be separate. You do not put a stress component at different point in one matrix.
So what's Tom saying there? Because I interpreted it as the opposite of what you just said.
Tom, what I'm talking about is that in that static stress matrix, the 3x3 matrix, they should not they put the tau xy power x and the sigma xs at different points. It's not at the same point. They're putting the stress component at different point in one matrix. That's the part that I said they're doing wrong. So in this graph, I don't see very clearly like longitudinal force and lateral force and cause shear and bending. Can you explain more like which point is shear stress you are calculating, which stress is?
We're looking at the device on number 5 and the flat plate that's attached to the back. That's what's going to get mounted to the body. If you want to explain a little bit more.
So the motor goes in here, lead through comes up here, and then the loading conditions up here. So it's a transverse shear going straight to the lead through, and also a bending moment going that way. So this mounting plate is getting pushed down and pulled out.
Okay.
So that and that, those 2 points are where the bending and
Okay. Okay, you can consider both points. If you don't know which point is more critical, you can calculate the stress component at each point and then compare and check the calculated result, which point actually turned out to be more maximum larger stress, but it's absolutely not correct to put like stress at each different point and put in one matrix. So, and also check your calculation about the shear stress and bending stress. And if you have like bending really that long arm, just think about the moment arm is that long. How is one for that sigma, the sigma is that small, right? Yeah, that one definitely check.
Would you recommend us choosing a singular point or doing two separate matrices for both points?
You can right now probably what I feel is that you don't really know which point is more critical, right? So what you can do is that the top point you do analysis, the side point you do analysis.
So two separate analyses.
Two separate,
Okay.
and then in the end, whichever point turn out to have larger, if you use bounding stress or maximum shear stress, which one has larger bounding stress or maximum shear stress, that is critical point. Right now, you don't know which one is more critical. You do the analysis and you calculate. Yeah.
For optimization programs, we give that the fancy name of search methods. You're just looking for it. He's kind of free-handed, more or less. Then you go off of what is the worst or best.
It's just a process of just picking a random point on the frame and calculating.
It's not random point. You need some analysis based on your based on your mechanical material understanding. Like you feel which point should be the candidates of the critical point.
Right.
And you don't know, you have several candidates. You don't know which one is actually more critical. You do calculation, prove it.
So you do all of them and then.
Yeah, right now you have two candidates. It's not a lot of work. I mean, and also if like at one point it's like bending stress dominant, well, you only have any, right? But it's mathematically wrong that you put the stress at different point and put in one matrix and do the calculation. Because if you think about the shear stress distribution caused by the transverse shear, and also the normal stress called the bending, the distribution is completely different on the cross section. I mean, let's say if you have a cross, let's use this, I don't know what's this as cross section, and shear stress is start from 0, maximum and neutral surface, and then back to 0, right? But if it's bending, is if I bending this way, top and bottom, they are maximum, neutral surface is 0. So I mean, why do you right? So it's like it's not like well anyway, it's not correct to put stress at different points. Is different point the stress their shear stress sigma is there the completely different distributed different way. So the place have maximum shear stress doesn't mean that it has maximum shear stress. The place have maximum shear stress doesn't mean it has maximum normal stress caused by bending. Right. So do separate. Okay. And yeah, I'll put 15.
15.
Oh, now I think I understand. So yeah, I understand what Tom said saying here. I think I agree. So put all the worst point at in one matrix and then you calculate results in more conservative. I agree. That you want to optimize way, yeah. Do you add what I said? Now I understand what Tom talking about. Yes. If you put the maximum shear stress and maximum normal stress and put in one matrix, actually you get much higher result than it's actually telling you your calculation is more conservative. Yes. So this one, just some small details I don't understand. Is like you have the SSSS and then some plus something. What does it mean?
What's it? Yeah, so Jarvis did the analysis on this. Is essentially S is it's like the baseline measurement, and so you have a baseline measurement and you compare the volume to that.
Okay. Yeah. No. Just need to because if people just see that they don't why you have SSSS and then plus minus.
Also, that text is awfully small.
Yeah, you do have to be careful that you are not combining two wordspace. Really, yeah. Any question for me?
No questions, pretty much everything I figured I got covered, but I do have just a few comments in terms of your, when it comes to like presentations and just a little advice from me to you in terms of, what happens when you're presenting to someone who's either from engineering and like academia or industry, whichever,